Thank you very much, John, for the kind introduction. It's a big pleasure to have the opportunity to give this talk today. I will talk about the global energy transformation, and my talk will particularly focus on some of the findings of the global energy assessment, which was carried out over the last 5 years and coordinated at the IIASA, but involving 300 authors and 200 reviewers that have been working together to make an assessment of the present state of the energy system, to explore major energy challenges, to look into transformational pathways, how to address those challenges, and to identify effective policies, their costs, but also the benefits that an energy transformation might bring about. I think another reason why perhaps to focus on the global energy assessment is that it's one of the many successful examples how science can inform policy making or policy in general. And in this context, particularly the Sustainable Energy for All initiative by the United Nations, which is actually also spearheaded here at the IIASA, in Vienna by UNIDO, particularly Director General Candy Keller and an expert group who have been working together on identifying 3 major global objectives for the year 2030, aspirational and ambitious objectives, but achievable in order to provide an entry point for the transformation of the system. So what are the main challenges? I mean, at the one hand, energy is, of course, fundamental for economic development. It's also fundamental for human well-being. It underpins all social activities. Yet the present system faces a number of challenges, particularly the 4 that I'm listing here. Perhaps foremost and most important is to address the lack of access of people, of impoverished people, people who are excluded from modern and clean energy services. Another challenge is to improve energy security in the world, in different regions as well as different countries, to limit air pollution and by that eradicate health impacts that are caused by low air quality. And finally, perhaps the biggest challenge is also to limit climate change to deep reductions of greenhouse gas emissions. And all of these challenges need to be solved simultaneously. And as I mentioned earlier, perhaps the biggest challenge or one of the most immediate challenges is energy access. The map that you see here shows people without access to electricity or clean cooking. I think it's quite nicely visible that where the hot spots are, it's particularly sub-Saharan Africa, South Asia and Pacific Asia, where together there are about 3 billion people without access to clean cooking and another 1.3 billion people without access to electricity. This is causing major health damages. And recent analysis indicates, analysis by many different groups indicate that in principle, energy access problem can be solved over the relative short term, provided that dedicated policies are introduced to mobilize the financial resources. Particularly investments between $35 and $40 billion are needed per year. This might sound like a big number, but actually it's a very small number. That's just 0.5% of the total investments at the moment into the energy system. And those investments would bring enormous immediate and short-term benefits in the order of 1 million lives saved each year between now and 2030. Energy access and the scientific evidence about that is becoming bigger is also an important contributor to outdoor air pollution. So the lack of access is not only causing health impacts, indoor health impacts affecting poor people, it's also contributing to outdoor air pollution. And in this slide we can see an extrapolation of the situation in the year 2030 coming from present air pollution policies. I think it's quite nicely visible that large parts of the world, if policies are not made more stringent, will be exceeding WHO health guidelines and will have much higher exposures than those guidelines would suggest. So what is needed is to not only improve the stringency for air pollution controls, but to combine those also with access policies to reduce health impacts in the order of 2.6 million lives saved each year. And that's the map of such a scenario by 2030. And as you can see, it is possible until 2030 by strengthening air pollution and access to stay below WHO guidelines actually in major parts of the world. The other challenge is, of course, climate change. In order to address climate change, it's necessary to reduce greenhouse gas emissions over a quite ambitious schedule. Over the short term, it will be necessary to slow down the growth of emissions, and emissions globally would need to peak relatively early, already by the year 2020 or around that. Afterwards, emissions would need to be reduced further to 30 to 70% of today's levels by 2050, and eventually, within this century, emissions need to come down to almost zero or even become negative. What does negative mean? Negative means that the energy system might become a sink instead of a source today, and this can be achieved through a combination, for example, of technologies like biomass, electricity generation, and carbon capture and storage, which would remove CO2 from the atmosphere and put it back there where it comes from, more or less into underground reservoirs. In order to achieve those environmental and social performance improvements of the system, it's necessary to fundamentally change the way energy is used at the moment. This requires changes at the demand side, but also changes at the supply side of the system. And this graph illustrates the development of primary energy in the future, an illustrative case for a transformed energy system in the long term. And one of the major options that is available, and which has also been emphasized in earlier sessions, are energy savings in order to reduce energy demands. So measures that would enhance efficiency, conservation, but also behavioral changes are extremely important, not only because they can the potential of those are very big. If you look at this slide, about 50% of the problem can be avoided to efficiency. It's also important because efficiency is one of the measures that brings multiple benefits. So any unit of energy that is not consumed is per definition pollution-free, has no greenhouse gases, and is also secure. Other important characteristic of a transformed system is the upscaling of renewables to about 50% by 2050. That's compared to 15% today. To phase out of oil in the long term and the reduction of oil use over the medium term to roughly half the today's level by 2050. There are a number of options which will also be important to improve the economics of the solution, particularly the combination of fossil fuels and carbon capture and storage will permit the use of fossil fuels over some time, and fossil fuels will be with us for some time. And if you look at this green wedge here, you can see the negative emissions that are created by biomass and CCS. I have just one slide, John, if you allow me to conclude. The policy costs that the transformation will depend a lot on how we prioritize those different objectives. You can see here costs of so-called single-minded approaches to the energy transformation. If you take only energy security, air pollution, or climate change as an entry point, and as you can see, those individual objectives differ quite a lot in terms of costs. Climate being the most expensive because they also, addressing climate change requires also most fundamental changes to the system. And what is not shown here in the slide, and actually that's the main message in terms of policy costs here, are integrated solutions. So solutions that try to address all of the objectives simultaneously are just marginally more expensive than climate change. And this is because of the many co-benefits that climate change would provide to address also those other objectives. So it's important to take those into account, and this means also significant changes in policy making today. Thank you.